All right, welcome. Today, we're going to tackle one of the most brilliant and, let's be honest, one of the most notorious ideas in all of math, the epsilon-delta definition of a limit. This is the bedrock concept that took calculus from being a bunch of cool tricks and turned it into the logical powerhouse it is today.
See, back in the early days, calculus worked, but nobody could really prove why it worked with 100% certainty. It had its critics, and one of them, Bishop Berkeley, had this amazing phrase for its core ideas. He called them the ghosts of departed quantities. It's a great line, right? It perfectly captures the problem. The whole thing felt a little spooky.
And that's the big problem, isn't it? How do you actually prove something is getting infinitely close to a number? I mean, getting closer sounds simple enough, but it's an idea based on movement and time. Math demands something more solid, something that's just plain true, no matter what. You had to find a way to lock it down logically. Yeah, to finally get rid of those ghosts, mathematicians knew they needed a totally rigorous foundation. The fuzzy idea of a number approaching another number just wasn't going to cut it. They needed something you could write down on paper, something cold, hard, and logical that could be proven without any shadow of a doubt.
And this is what they came up with. Okay, I know. At first glance, that looks like a total nightmare, just a wall of Greek letters and symbols. But here's the absolutely brilliant part. We don't have to think about it like that. We can reframe it into something way more fun.
So let's just forget about it as a dry definition for a second. Let's reframe it. What if we thought of it as a game? A challenge between two players that perfectly explains the logic of what's going on. So every game needs players, right? Meet ours. On one side, you've got the skeptic. Their job is to be difficult. They're trying to find some tiny level of precision, some microscopic target that the other player can't possibly hit. And on the other side, you have the prover, who is totally confident. They claim they can meet any challenge the skeptic can dream up. All right, game on. Let's see how a round of this actually works. The skeptic gets to go first. So the skeptic steps up. They pick a value called epsilon, which is basically just the margin of error they'll allow. It's the size of the target. They're saying, okay, prover, I bet you can't guarantee your function's answer is within 0.1 of the real limit. Go on, try. But the prosaver, totally unfazed. They fire back with something called delta, which is a restriction on the input values they're allowed to use. They're basically saying, oh, that's easy. As long as I keep my starting numbers within this even smaller range, I guarantee my final answer will land inside your target zone. Okay, but the skeptic isn't going to make it that easy. They crank up the difficulty. They make the target ridiculously small. The new epsilon is tiny. The skeptic is trying to find a weak spot, a challenge so demanding that the prover just has to give up. And boom, the prover has an answer right away. Are you seeing the pattern here? It seems like no matter what crazy small epsilon the skeptic throws out, the prover has a corresponding delta ready to go. And that gets to the real heart of the game. See, winning this game isn't about surviving one round or even 100 rounds. The prover only wins, truly wins, if they can slap down a single formula on the table, a master strategy that takes any epsilon the skeptic could possibly imagine, no matter how insane, and automatically spits out a delta that wins. Every single time. So the big question is, how does the prover build this unbeatable strategy? Well, it's all in the algebra. Let's actually walk through a proof with a simple example and see exactly how the prover creates their winning formula. Okay, let's get our hands dirty. We want to prove that as x gets close to 3, the function 2x plus 1 gets close to 7. Step 1. We start with the skeptic's challenge. We need to show the distance between our function and the limit. So I'll get 2x plus 1 minus 7 is less than any epsilon. That's our target. Step 2. Now, the prover needs to link this output problem back to an input restriction involving x and 3. So we do some algebra. 2x plus 1 minus 7 simplifies to 2x minus 6. Then we can just factor out a 2, which gives us 2 times x minus 3. And we can pull that 2 outside the absolute value. So we have 2 times modulus x minus 3 is less than epsilon. Now just divide both sides by 2, and we get modulus x minus 3 is less than epsilon over 2. And right there, that's it. That's the magic moment. Step 3. Look what we did. We connected the prover's input, modulus x minus 3, to the skeptic's challenge, epsilon. We found the winning strategy. The prover just has to declare, my delta will always be whatever your epsilon is divided by 2. Step 4. And that formula, delta equals epsilon over 2, is the master key. It's the prover's secret weapon. The game is over. The prover has won. Let's try to picture what's happening.
Imagine the skeptic draws two horizontal lines, one just above the limit L and one just below it. The space between those lines is the epsilon band. It's the target zone. The skeptic is daring the prover to keep the entire function graph trapped inside that narrow band.
And the prover's formula, that delta equals epsilon over 2 we just found, that gives them the exact width for a vertical target zone around their input, A. It creates a delta band. As long as they only pick x values from inside that vertical band, they have mathematically guaranteed that the function's output will land squarely inside the skeptic's horizontal epsilon band. It's a perfect system. No matter how much the skeptic shrinks their band, the prover's formula finds a delta band that's small enough to win. So, I get it. This might all feel like a super abstract, nerdy little game. But you have to understand, the importance of this is massive. This game is what takes calculus from a bunch of useful but shaky ideas and turns it into a fortress of logical certainty.
But let's just think about this for a second. What if this game didn't exist? What if nobody ever figured this out, and we were all still just hoping for the best, still building our understanding of the universe on those vague, spooky ghosts? Think about it. Every single calculation for a bridge's structural integrity, or a rocket's trajectory to Mars, or even the financial models that run our entire economy, they all depend on calculus being right. Without this rigorous little game, all of that would be built on a guess, on a ghost. The Epsilon-Delta game isn't just a clever puzzle. It's the solid ground that our entire modern technological world is built on.